The world insists 19th century cities ran on horses and steam. But when you measure a single civic arch spanning 15 meters, when you compare the uniform street grids from St. Petersburg to San Francisco, nothing adds up. Why design cathedrals for carriages? What moves at these speeds? And why does every global capital speak in the same cubic code? The answer, hidden beneath official history, begins with a question most historians refuse to ask. Measured in cold stone and iron, the evidence stands silent. A single civic arch, 15 meters from end to end, dwarfs the scale of anything a horse-drawn carriage could demand. Royal Institute of British Architects drawings from the 1960s record these spans in black ink, the numbers unblinking, 12, 14, sometimes 15 meters, repeated across city halls, post offices, and railway termini from London to Chicago. These are not isolated anomalies. In Antwerp, the main hall's vault stretches 13 meters without a central pillar. In St. Pancras, iron ribs leap across 12 meters at regular intervals, forming a rhythm that echoes through the city's bones. The same proportions surface in Paris, Vienna, and New York. Arches wide enough to swallow entire traffic lanes, vaults high enough for air to hang undisturbed above the heads of any crowd. Contractors' ledgers from the period show cost overruns, not from scarcity, but from the sheer mass of material demanded by these designs. Stone blocks quarried by the ton, ironwork forged in spans that defy pedestrian logic. No carriage, no steam tram, no foot traffic justifies this kind of overcapacity. The numbers refuse to shrink to fit the official story. What moves through a 15-meter arch at speed? What force required such uniformity, city after city, continent after continent? The measurements are not folklore. They are cut into the very fabric of the old world, demanding an explanation that matches their scale. Blueprints from Boston to Budapest tell the same story. City grids snap into place with uncanny precision, blocks measured out in uniform rectangles, boulevards radiating from central nodes, and public squares spaced at regular intervals like clockwork. The plans for St. Louis, drafted in 1850, match the layouts of Kiev and Milan, down to the meter. In Australia, Adelaide city centre mirrors the symmetry of Philadelphia, both anchored by oversized avenues and identical civic axes. These are not the chaotic streets of medieval towns, but calculated diagrams, as if stamped from a single template. The repetition is relentless. Railway terminals align with city halls, always at the heart of the grid, surrounded by identical rings of government buildings, libraries, and post offices. Even the distances between major intersections repeat across continents, measured in multiples of 200 meters and 400 meters, over and over. No local tradition explains this. No regional style justifies the global sameness. The evidence points to a single organizing principle, a hidden logic behind the bricks and mortar. These cities were not built for slow, meandering travel. Every line, every axis, every oversized boulevard hints at a network designed for speed, an invisible system layered beneath the official story. The uniformity is not aesthetic, it is functional. This is the grammar of a world wired for instantaneous movement, disguised beneath the surface of everyday streets. In the archives of the British Library, a single plate drawing from the 1860s sits buried in a stack of technical diagrams. The label reads simply, GPO basement conduit sectional elevation. The cross-section is exact. Brass pipe, wall thickness measured, bore diameter marked in black ink, 820 millimeters. That is not a male chute. That is not a vent. That is the width of a human torso, with room to spare. The dimensions repeat across multiple entries, 600 millimeters, 900 millimeters, never less. These are not outliers. The ledgers from the General Post Office list purchase orders for brass tubing by the ton, delivered in lengths up to 12 meters. Contractors' notes mention reinforced floor slabs and special hoisting gear to lower the sections into place. Photographs from the period, sepia and grainy, show workers dwarfed by the open mouths of these conduits, arms outstretched against the curve of the metal. No official record explains why a city's post office would require pipes large enough for a person to crawl through. The scale is undeniable. It is not theory, it is measurement. The evidence sits in the open, stamped with the insignia of the crown, catalogued and forgotten. If these were only for letters, the excess is absurd. If they were built for something else, something that demanded human scale passage at speed, the design makes brutal mechanical sense. The question is not whether the pipes exist. The question is what, or who, they were meant to move. In 1810, George Medhurst filed a patent for moving people and goods through tubes using nothing but air pressure. His diagrams show a sealed conduit, a carriage suspended inside, and a difference in atmospheric pressure at each end. The concept was simple. Create a vacuum ahead of the capsule, force compressed air behind it, and let physics do the rest. By the 1860s, engineers in London and Paris were experimenting with brass pipes and pressure chambers, but official records limit these to male. The scale of the tubes found in civic blueprints, 820 millimeters, sometimes nearly 1 meter, contradicts that story. These dimensions match a human body, not a letter. Pressure differentials in a closed system can move objects at tremendous speed. A drop of 1/10 of an atmosphere across a 20-meter tube is enough to accelerate a payload faster than any horse-drawn carriage. The Medhurst model was never built to full size for passengers, according to mainstream accounts. Yet the purchase orders for reinforced brass, the custom hoisting gear, and the repeated reference to person-sized bore diameters suggest a more ambitious application. If the system was designed for organic transit, every element, the pipe's thickness, the sealing gaskets, and the airlocks, had to be engineered for human safety. The mechanics are plausible. The evidence sits in the ledgers and the blueprints, waiting for someone to connect the pressure equations to the architecture. The next question is, how did a person enter the system without decompression or injury? That required a specialized interface, one hidden in plain sight. Inside the Bradbury building, the elevator cages hang suspended in an atrium of iron and glass. Each one is a lattice of interlocked steel and copper, doors sliding with a weight that feels deliberate. The Rookery in Chicago repeats the pattern: wrought iron mesh, heavy brass rails, and polished copper windings coiled around the elevator motors. These are not decorative flourishes. They are the visible surface of a machine built for more than vertical movement. In the sub-basement, photographs from the 1890s show deep elevator pits lined with thick copper plates. At the lowest level, a bank of dynamos sits bolted to the foundation, their armatures wrapped in copper wire as thick as a man's thumb. Maintenance ledgers from the period list regular replacements for copper brushes and commutators. Quantities measured in pounds, not ounces. The current ran through every part of the system, grounding the cages and charging the rails. Elevator operators reported a low hum beneath their feet, barely audible but constant, when the machinery was engaged. The mechanics are precise. The elevator cage itself forms a Faraday enclosure, isolating the occupant from external electromagnetic fields. When the cage descends to the lowest stop, copper contacts align with plates embedded in the pit floor. The circuit closes and the dynamo surges. In Bradbury's original blueprints, the elevator shaft is drawn as a hollow column, lined with conductive metal from top to bottom. The design is not accidental. Every element, the copper winding, the iron mesh, the grounded rail, serves to channel and modulate current and prepares the body for a shift in frequency. These elevators were never meant to stop at the lobby. They were local interfaces, entry points into a larger network. The evidence sits in the hardware: oversized counterweights, redundant ground lines, and copper coils far beyond the needs of simple hoisting. The cages are not relics. They are machines built to interact with something hidden beneath the city's surface, waiting for the right conditions to activate. Beneath the vaulted ceilings of Grand Central, sound moves in ways that defy ordinary explanation. Step into the main concourse and a whisper travels from one corner to the next, carried along the curve of Guastavino tilework. The blueprints stored in the New York Public Library archives reveal more than decorative flourishes. Every arch, every panel of quartz-veined marble, every copper ridge in the roof is calculated. Acoustic spectrograms of the terminal's central hall show resonance peaks that align with the geometry of the vault, a frequency map embedded in stone. The same patterns repeat in St. Pancras, where iron trusses span the length of the train shed, forming a chamber that amplifies and sustains sound waves. Antwerp Central's dome, lined with bands of copper and blocks of quartz-heavy granite, hums with a low vibration when struck. Conservation reports from Belgian archives list the mineral composition of these stones, noting the unusual density and piezoelectric qualities of the quartz veins. These terminals are more than transit points. Their dimensions, their materials, and their placement at the heart of the city grid suggest a purpose far beyond the movement of trains. The plans for Grand Central accessioned by the New York Public Library show a network of sub-basements and sealed corridors radiating from the main hall, spaces never open to the public, lined with the same copper sheeting found in the roof above. The Royal Institute of British Architects' drawings for St. Pancras echo this arrangement, with hidden galleries beneath the platform and thick-walled chambers at each end of the vault. In each case, the architecture forms a resonance cavity, tuned to specific frequencies by the interplay of stone, metal, and empty air. These are not accidents of engineering. The evidence sits in the geometry and the mineral record, in the way sound lingers and amplifies within the great halls. The terminals functioned as the electromagnetic hubs of the network, city-scale nodes where frequency and pressure could be harnessed for instantaneous transit. The grandeur of the space is not for spectacle, but for function. A machine disguised as a cathedral, humming quietly beneath the noise of daily life. Excavation photographs from the 1860s and 1870s capture a world beneath the city. Brick-lined tunnels stretching in straight lines, curving at impossible angles, vanishing into darkness. In London, a plate dated 1865 from the Metropolitan Railway archives shows workers standing shoulder to shoulder inside a tunnel nearly 3 meters high. The brickwork pristine, mortar joints tight, no soot or water stains to suggest age. The caption reads, "Initial opening Holborn Viaduct," yet no construction debris is visible. only the smooth, finished surface of a passageway that looks as though it had always existed. In New York, an 1872 stereograph labeled Subterranean Passage, City Hall Vicinity reveals an arched corridor lined with glazed brick, the floor swept clean, iron rails absent. The date predates the official subway by 3 decades. Both images share a peculiar detail. The curvature and finish of the vaults match the dimensions recorded in post office and terminal blueprints. 2.7 meters wide and 2.5 meters high, consistent from city to city. Mason marks etched into the bricks repeat across continents, the same symbols found in Antwerp and Boston. Age indicators, lime efflorescence, and mineral streaks suggest the tunnels predate the streets above, their courses unbroken by later foundations. These are not sewers, not utility conduits, but sealed channels, their purpose unlisted in municipal records. The photographic evidence is silent, but unyielding. Each image, stamped with a date and place, documents a network that was already in place before the first subway train ran, before the official story began. The tunnels bear the signature of a vanished system, engineered, finished, and then hidden in plain sight. Inside the mansions of the old world, the evidence is colder and quieter than stone. Step into a drawing room lined with walnut and velvet, and the fireplace stands at the center, massive, ornate, yet strangely inert. The hearth is lined with copper or brass, plates set flush against the brick, their surfaces dulled by age but untouched by soot. The flue rises straight up, but the chimney ends in a sealed cap, with no vent to the outside, no trace of smoke ever passing through. Conservation notes from estates in New York and Vienna list these fireplaces as non-functional, their purpose a mystery even to restoration architects. In the Vanderbilt mansion, the main hall hearth measures nearly 2 meters across, lined with a grid of conductive metal, the plates bolted into the masonry as if meant to carry current, not heat. There are no burn marks, no ash, only the faint green tinge of oxidized copper. Floor plans from the 1880s show these hearths repeating through every major room, each one connected by a web of narrow conduits running beneath the floorboards. In some cases, the plates are engraved with geometric patterns, hexagons, spirals, and intersecting lines that match diagrams found in technical manuals for early electrical experiments. The absence of a true chimney, the presence of metal grids, and the sealed construction all point away from heating and toward another function entirely. In these rooms, the fireplace was not a source of warmth, but a private node, an entry point for something that moved not by fire, but by frequency. The motive is clear: instant movement, untraceable and untaxed. A network that reached not just across cities, but into the heart of every home. Profit is the only constant in the aftermath of empire. By the 1870s, the names Vanderbilt, Morgan, Carnegie, and Rockefeller were stamped across every major rail line, depot, and coalfield in North America. Each acquisition followed the same pattern: buy up the bankrupt lines, seize the city terminals, and absorb the rights of way that once linked the heart of every metropolis. In 1869, Vanderbilt's New York Central swallowed the Hudson River Railroad, locking down the main artery into Manhattan. Morgan's syndicate engineered the Erie War, flooding the market with paper shares until every rival collapsed. Carnegie consolidated the steel that rebuilt the rails, while Rockefeller's Standard Oil controlled the fuel that powered the new machines. The timelines are not subtle. Between 1865 and 1890, over 2/3 of the nation's rail mileage passed into the hands of these four men. Their ledgers show not just lines and stations, but entire city grids, including the tunnels and terminals that had once served a different purpose. The motive is written in the margins. Instant, untaxed movement is unprofitable. Slow the flow, meter the access, and every mile becomes a toll gate. The cover story was elegant, steam, smoke, and progress. The reality was consolidation and erasure of a technology that could not be taxed or controlled. The names are public, the deeds are filed. The only missing element is the will to investigate. The checklist is simple. Follow the deeds, measure the tunnels, question the upgrades. The evidence is still buried beneath the rails, waiting for those willing to dig. Today, the deepest infrastructure beneath our cities remains sealed, its true origins debated, and its purpose obscured. As urban archaeologists expose layers of forgotten engineering, mainstream history insists on horse-drawn certainty. But unanswered questions persist, fueling a hunger for suppressed knowledge. The more we retrofit the past, the more we risk erasing the blueprint for what is possible. What is hidden beneath us may determine how far we are allowed to go. Share your theory below.